let me check if this is possible. Wait, while grabbing this. That one. No, this one. This is the better one. Okay. So, okay. That's what I mentioned. Good enough to see me, but bad enough that they regret not coming. That's the idea. This is the first, and here's like, they can't see this. No, doesn't matter. Okay, I'll start 1 minute later. So, I have to do class today, that's fine. Whoever who came slightly late, like, I'm not going to use my laptop today, but I'll just use this stack, okay? So, you can find it like a whole bunch of places, my own website, like the Quarkus website, and the announcement. So that's it. And today, I allow any type of recording, including voice or like visually. I don't feel like visually will help like that much, but if you feel like you missed something and you need like my voice to walk you through this entire deck once again after class, I'm fine with it. Otherwise, I'm just like doing the, wait, are there anyone even watching? I hope not. Great. Yeah, I'm kind of streaming myself, so I'll post like the YouTube streaming link. So at least you can rewatch anything if you kind of missed it. That's the overall idea. And like one last thing, which is I'll clearly mention what's covered and what's not covered in Masood materials. And just for example, like elements of game theory, some of those parts are not, like some of them are important, but Masood didn't really place them in his slides. And most importantly, that's because of, I guess it's Larrett's fault, who's like the author of the textbook. So I can't really find any other ways to tell you like, hey, we need to learn this or not learn it. So instead, I'll write everything as optional if it's not directly taught in class. But some of them include decision theory. I'll go through them like slightly, and that's the idea. In between, when it's around 6 o'clock, feel free to give me a heads up, like, hey, Lawrence, like it's 6. Then I'll give you like a 5-minute break, and we'll come back. So I'm not sure how long it will take since I wrote this deck for about 2 weeks-ish. I hope it's not like too much overtime, but maybe we'll finish it earlier, maybe later. We'll figure out. Like, still aim for 6:55 to end everything. But if we finish it earlier, then everyone's good to go. Okay. Okay. So hopefully every time I'm just going to start with this. So. Okay. And why am I wearing this? Because it's close to Valentine's Day. Too bad you don't really have a class next week, or I'll wear it all red for the Lunar New Year. Okay, let's start. Yeah, so first of all, yeah, game theory. I'm going to cover like everything about game theory, everything which shall be tested, yes or no, like everything could be in this class. So it's like started from everything we learned so far from oligopoly until repeated games, which I know we're already ahead of schedule if you're in my tutorial for quite a while, because what I'm talking about later for repeated games, which will be the first thing Masood's going to teach all of you right after reading week. But sadly, right after that, we only have one more tutorial left, and I will use that for a grand review for your term test 3. So because of that, today I'm just going to cover everything you might need to know, since I'm not going to teach anything new next time, okay? So that's the plan. Here we go. So first of all, remember, so when do we use oligopoly? In my session, I did talk about when you got some kind of Herfindahl index, HHI, which is around like 1,500 to 2,500-ish, which means that you got like 5 or fewer firms which are important enough. In that case, you care about each other's decisions. So that's something which links to who are the players. Yeah, that's something kind of important. And also, we know like Kunur competition, we do quantity competition. And for Bertrand competition, we compete with price. And for Stack Overflow competition, it's like a slightly different thing. Stack Overflow model is talking about someone's like before, someone came after. It's like a leader and follower scenario with quantity. So those are what I expect you to know pretty well. But then we'll talk about everything game theory. So game theory in class, I first mentioned the three things you need to know from class. One is called players, like who are the players, who's playing this game. Second, what are the strategies you can actually pick? And third, what are the payoffs based on the mix of your strategies? Okay, so who are the players? I came up with like a fun idea like in my own notes. So for example, if the brothers broke away like based at home, and the angry mom came out and tried to like take a broomstick, try to beat someone up, like who did this? Okay, the brothers can either admit it together so they get like a lighter punishment, or blame it on each other while the other admit it, or blame on each other so they go like both get beaten up harshly. So that's kind of the overall idea of like a random story at home. Okay, yeah, I'm not sure about like talking about beating or not is good idea, but that's general story. Okay, so then that's the thing. Okay, the mom's the one who beat the kids. So is the mom a player? The answer is no. Why? Because, okay, are they going to blame each other or are they going to admit it? These decisions are only made by the brothers, not the mom. The mom is just some kind of like executioner in the end who's trying to give you the outcome, give you the payoffs. So because of that, get the idea. If you are not even important in an entire game, you are not a player. Okay? Just remember that. I did talk about actually we should split two things, which is one is called actions. Action is what do I do? Admit or deny, like confess or not. Those are actions, what you can do. Strategies is like a combination of the actions, but in our course material, most of the time, especially in this session, we consider these two things nearly equal, okay? For this class, just this class only. If you're taking 316, 325, or 1201, which is the master level econ classes, you will see totally different things from actions to strategy. They're different in the future. But right now, for example, if we're playing like static games, people talk about, hey, we choose our option at the same time. We make our action at the same time. It doesn't really matter. So in that case, strategy is your action, action is your strategy. Okay, that's the only case. Wherever we have like a before-after scenario, sometimes we need to consider it slightly different. Okay, that's generally the rule. So in this course, when we talk about strategies, it's the same thing as I'm picking an action which I'm going to do. Okay, that's strategy. Next, outcomes. This is also something else which we're not going to talk about that much. So outcomes, for example, if we get strategies SI and SJ, so for example, like, okay, so we kind of figure out like how the strategies interact with each other. So with your strategies, like mixing up with my strategies, there will be like a final action set. And based on these actions and these specific times, like these specific points, we will have like two poles of, oh, okay, so the outcome is enter, exit, or exit, exit, enter, enter, things like that. Those are called outcomes. Each outcome gives you one payoff. It shouldn't give you multiple payoffs. It's like each outcome gives you one payoff. Okay, that's the general idea. So those are the elements of a game. Yeah, I spent some time on this just to make sure everyone understands it. Okay, then now we can turn to like the third part, which is building toward the equilibrium. Now you'll see some harmful math. So what are we doing with these math? So generally, I'll talk about, so BR stands for batch response. Everything with an S stands for strategy, okay? And just in case, this will not only be my session, but like anyone else's session, if you see S minus I and SI, what does it mean? SI stands for the strategy of player I, okay? S minus I stands for the strategy of everyone else, okay? Which is like not me, everyone else. So normally if this is one player, it could be the same thing as SJ. But if it's multiple players, you can assume that's like kind of a matrix, talk about many different players all together, staying on the same strategy without moving. That's the overall idea. Okay. So yeah, that's a So best response stands for, like the capital S stands for every single possible strategy set. Okay, so each strategy is like, okay, I'm playing, I will play exit if this happens, I will play enter if that happens. So that's generally what I'm thinking for like a small s. The big S is anything you can ever choose, like exit, exit, enter, 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 exit, enter, enter. Like all four options, they belong to the big S, which is everything you can select. Okay. And of course, if you've got like a big S with a minus I, which stands for everyone else got those like four options. So you got, for example, if you got like 10 players and 9 of them belong to that thing, you are not going to write out 4 with a degree of 9. Yeah, you're not going to write that many things out. We're just talking about they belong to that big S group, okay? So that's just how you read this. And U stands for utility, which also could be the pie part, which are about your payoffs. And if you see anything with a star, which stands for that's the best part, that's the best response, that's the optimal scenario, okay? And if you see a prime, like a dot there, which stands for this is something else, which also belongs to the strategy we're talking about, but it's not the one we're picking right now. Okay, so again, if you see anything with a star, which stands for it's already an optimum at like of a specific scenario, the best scenario already. And if you see as something like a prime, which stands for just randomly anything else, anything's okay. Okay, that's a thought. So what we need to learn from like this session is best response, which stands for if given someone else, if J is picking a specific strategy, what are you going to do to maximize your utility, to maximize your payoff? Okay, that's best response, and we kind of cover it multiple times. But what is kind of slightly new from this part is dominant strategies. So here you see like a 5x5 table, and this one belongs to the practice question 1 of 5x5 game. It looks horrible, but we can actually figure things out. So 2 things. Number 1, dominant strategy stands for if I have one strategy that no matter what, I will always pick. In other words, no matter how others choose, it is like if you choose one specific strategy and it's always the best response, I'll repeat, if you choose one strategy and it's always the best response, it is a dominant strategy, okay? Yeah, ideal, right? And of course, there's the other scenario, which is called dominated strategies. Now I use the word strictly dominated strategies. I want to make that sign smaller, not smaller equal, smaller. Why am I going to talk about strictly? For example, if today you're talking about, hey, like after making one decision, I'm always getting 0 payoff. Like for example, if we're talking about like enter or exit the market, and the second player decides like the number of quantity, like something about quantity. Okay, in that case, if they choose exit, their payoff is always 0, right? If I already choose exit, it doesn't really matter anymore. So what happens in the future is none of my business. But in that 0, and you say, hey, 0 is smaller or equal to 0. So I am dominated by myself in all other scenarios and vice versa. In that case, if you can delete yourself if it's equal, then we don't even play a game, right? Then you see things like, oh, okay, 0 is larger or equal to 0. I'm crossing that out. Then I'm crossing almost everything out in the case that I'm exiting the market. But that doesn't make sense in game theory. So I talk to everyone as strictly dominant strategy, means that there's something which strictly becomes slightly lower than others. So let's take a look at this game. And I intentionally designed it. I'll tell you the answer first. It's about we cross a row off, we cross a column off, and it could be repeated in different ways, okay? So you don't really need to look at it like for multiple seconds and like, I don't really know where to cross out. So here we go. Let's take a look at who is dominated. Okay. So see, here's R stands for row, like row 1, row 2, row 5, and column 1 to 5. So let's take a look at who am I going to cross out first? Row 1, okay. So we compare row 1 versus row 2. So if I'm player 1, row 2, like, okay, so now if player 2 chooses C1, I am player 1, row 2 gets me 4, row 1 gets me 3. So 3 is worse than 4, right? Again, C2, 0 is worse than 1. -4 is worse than -3. -2 is worse than -1. -5 is worse than -4. In that case, every single possible scenario of R1 is worse than R2. Okay? Makes sense, right? So in that case, we call it R1 is strictly dominated by R2. That's it. R1 is strictly dominated by R2. So that just happens as a direct way of telling you, okay, it's dominated. Okay, any questions? It should be easy enough, right? Then we'll go with something a little bit further. So, right. How about like what's next? Actually, without crossing this out, we couldn't really find something larger than the other, right? So for example, if you're talking about C1 and C2, you're like, yeah, -4 is worse than -3, 4 -4 smaller than 3, 0 smaller than 2, 1 smaller than 9. But you see, here's like a 10, and here's a 0. You cannot say C1 is dominated by C2. But instead, there's a thing called iteratively dominated. This is optional, but let's just assume that everyone can read this idea directly. So I just talked about this. This is called iterated dominance. What does it mean? Which means that I assume that you know who's dominated. So I assume that you're smart enough to know what you shouldn't play. So I can, based on your knowledge, to work on my. This is like, I always talk about the story. Like there's like a two Chinese philosopher. One's like, I feel like the fish looks happy. The second one's like, how do you know that? I don't feel like that. And the third one's like, you're not me. Iteratively going on and on. That's the logic of iterative dominance. Okay. So in class, we're not going to cover that word, but you just need to know this idea of iterative dominance. So if that's the case, now we know that player 1 will never play R1. That's now the general knowledge of everyone. Okay, good. Okay, in that case, okay, so 1 smaller than 9, 0 smaller than 2, same for the R4 and R5. Now we can kill C1, right? So now we can cross out C1, and this one, I call it iterated dominance. So I write ID. And the dominance, I just write like a D, okay? D. So this one's like R1 is dominated by R2. No, this is not how you normally write it, but I'm just being lazy. And in this case, this is C1 is iteratively dominated by C2, right? Yeah, C2. So in that case, we can continue the entire game like over and over. So let's just finish this entire thing. So again, it's like, okay, 5 better than 1, -2 better than -3, 0 better than this one, and -3 better than -4. So the same thing for R2, it is iteratively dominated. Like R2 is worse than R3. And the same story. Like you can just if you're missing like what I'm doing, look at the last page, page 18, 7.1, the 5x5 game. And same thing, like see, like 2 worse than 10, -3 worse than -2, and so on. So we also got this crossed out. Same thing. I just simply use purple for everything here. Like C2 is worse than C3. And with the same idea, you kind of cross this one out as well. Worse than R4. And the last one is the zeros. Like, okay, so -2 is always worse than the -1 or 1. So C3 is iteratively dominated by C4. Okay? Questions? So just remember, in this case, we only keep this tiny box left. This is specifying. Okay, questions?
So no matter what the matrix is, like how long, you always end up with like
Smaller ones?
Yeah, like the small, like how small.
The answer is it depends. If I'm going to torture all of you for your midterm exams, I'll give you a matrix that you cannot dominate anyone else. For example, if I give you like 1, 1, 1, 1, if I give you everything in the horizontal version, okay? So think of this case. Just imagine everything down here is all zeros, okay? And everyone else here is like 1, 1, 1, 1, 1, 1, 1, 1. So there is always one case that you cannot dominate, right? So in that case, you can't make this even smaller, right? Yeah. So in short, how small can it be? The answer is it depends on how many times you can cross things out until it's small enough. So we don't know. You need to solve it yourself, okay? And hopefully we wouldn't do this in the exam. So yeah, so we shall make it slightly smaller in different ways. So at least you can solve it. It's not fun that I give you like a 10 times 10 matrix that you can't even solve it. And yeah, and both Masood and I will receive a whole bunch of email telling us like the exam's too hard, we need to work harder on everything else. We had discussions about those. So we'll make sure things are doable, okay? Yeah. Okay, so any other questions about dominance and iterated dominance? All good? Keep track of the time. Okay, great. We're ahead of schedule for a bit. So, okay, so of course, this tiny block boxes matching pennies, right? If you remember that, which is like a zero-sum game, or the penalty kick, like I win, you lose, you win, I lose. And that's how the entire game theory idea started. Okay, so originally game theory is all about zero-sum games. Because like originally, we don't really think of scenarios that both there are like a lose-lose or win-win scenario. But later on, it also kind of belongs to what Nash did, which pushed everything all the way until we talk about, hey, there are scenarios which are not zero-sum. But here, this is a case that if you get an idea, it's kind of symmetric. And for matching pennies, we know 0.5, 0.5, 0.5, 0.5 is one of the mixed strategy Nash equilibrium. And if you forgot what that means, we'll have something else to practice slightly later, okay? Yeah, so best response, dominant strategy, which means the best thing. Oh, by the way, are there dominant strategies in this game? Just a random question. Are there any dominant? No, right? Yeah, everyone's shaking their heads. Because if there are dominant strategies, we don't need to cross everything out like one by one. But like, instead of crossing out, I'll tell you, I always pick R1, right? Things like that. So since there are nothing like that, we can't just simply say, I will pick this forever. Instead, we need to start crossing things out until it's small enough for us to find the solution. Okay. And dominated strategies, iteratively dominated strategies. And finally, what I am doing right here is called IDSDS. Okay, so what does that mean? So verbally, it's called iterated dominance of dominated strategies. And strictly dominated strategy. So I kind of like wrote it out right here. It's just telling you like I keep on crossing things out based on I think you know you shouldn't play that, and you think I know I shouldn't play this as well. So based on that knowledge, on and on until there are only something else we both believe that each other can ever play at least once in some scenario. Okay, so this entire thing is called IDSDS. You will learn it if you're taking Econ 303, 316, and 326, and master level and PhD level Econ. Okay, but it's just like a heads up since Masood just talked about this without telling you what that is. So I just let you know how we name it. Okay. So and finally we're heading to Nash equilibrium. Of course, this is not we can't get the so-called pure strategy Nash equilibrium. Oh, and I almost forgot. For dominating stuff, there is something called mixed strategy dominance. Which means that I can say things like maybe R1 is dominated by a mixed strategy of half and half from R2 and R3. Those are the difficult things we're not going to cover in this class. So domination in this class should be directly identifiable numbers. One is smaller than the other, okay? So I can be dominated by the mixed strategy of these two things. That will be advanced level classes. But get to know it happens, okay? Just a heads up. Nash equilibrium stands for you are mutual best responses, and you can think about it. If you are a best response, you will not be crossed out, right? If one of the strategy is a best response, you will not be crossed out. And of course, in this case, R4, we know if I am someone who's playing R4 and R5, I'm player 1. Sorry, C4 is not dominated. Okay, so in this case, if player 2 plays C4, player 1 picks R4. Player 2 plays C5, player 1 plays R5. Same thing for the other ones. So in this case, you didn't underline two things at the same time. So there are no pure strategy Nash equilibrium. But of course, if we take a look at everyone's favorite prisoner's dilemma, it's kind of clear, right? So number one, silent versus testify. So if you're playing silent, if the other one's playing silent, you're comparing -5 and 0. So you will testify. And if the other one testify -20 and -10, you pick -10. The same logic applies symmetrically. So testify, or it's in other words confess, admit, is the same thing, which is the Nash equilibrium. Okay, we just call it NE. I wouldn't know if I accidentally wrote please find ONEs in this scenario. Okay, so that means Nash equilibrium. Okay, so yeah, so in that case, we can also say since you always play testify, so testify is the dominant strategy for both players. And silent is kind of crossed out. I'm not really crossing out. I'm just slightly writing that line. Silent is the dominated strategy here. Okay. Okay. So if it's only this tiny box, then that's it. But sometimes we also play something else, which looks kind of fun. Okay. So now first remove this line for a bit, and let's add in a few more options, which is called nuke. It's -100 for all of you, which means that, okay, now the two prisoners are actually getting, they are caught and they are asked, what happens? So if someone's not happy, each of these countries, they have their nuclear weapon ready to bombard the entire area, including themselves. So everyone will be killed, the game's over. That's it. We call it nuke. Okay. So that's something which looks horrible and stupid. No one's going to pick -100, right? Think about this. This is something fun. If someone's playing nuke, what is your best response? Or does it not matter at all? It doesn't matter, right? Because no matter what you choose, you are -100, right? You're always -100. So if they play nuke, you're always -100. And same thing, if you play nuke, they're not going to choose anything since nothing matters. So in other words, in this specific game, nuke is also Nash equilibrium. Okay? This is also NE. But it doesn't make sense? Maybe, but maybe not. Because remember, why are we talking about Nash equilibrium? It's about if I pick this spot since the beginning, there will be no deviation from this point by any one player, which means that the result wouldn't get better if you didn't choose nuke, or if I didn't choose nuke. It only changes if both of us change our options, but that is out of the scope of Nash equilibrium, okay? So no one player can remove this equilibrium by switching to something else, okay? So, right, but of course, if you're asking, hey, so is nuke the dominant strategy? No, it's not. Of course not. The dominant strategy is still T for testify. Why? Because if you choose nuke, these three options are indifferent. But if you choose T for forever, you will still hey, actually this is something playable, right? Even though you got -100, -100, you're still underlying yourself. So T is the dominant strategy, and that happens for both of them. It doesn't mean that they must choose testify, but it's the thing that this is a Nash equilibrium people normally talk about. But we just get to know there's another Nash equilibrium here. And I will keep this thing right here because we will need it sometime later we can also talk about, hey, if we're not following my advice of doing this or that, we can have two Nash equilibria. So I will pick the one we both don't love. So you better listen to me. If not, we'll go on that way. Since it's a Nash equilibrium, it's playable, okay? So get to know, Nash equilibrium doesn't mean that it needs to be something smart. It could be something that looks really dumb, but no one can change it, okay? Elections also happen like that. So, well, it happens. Any questions so far? If not, let's move on. Yeah, so here, I actually added something fun. Yeah, okay, so you can relax for a little bit. Let's take a 5-minute not a break time, but I'm just going to talk about some random stories about John Nash. Okay, so yeah, people talk about A Beautiful Mind and talking about like, hey, like did Nash really talk about game theory when he's in a bar or something? The answer is hopefully not, because like according to all other people who got to know Nash well, like the movie kind of added a whole bunch of different things in it, including like he's actually like he got like schizophrenia in a different way than how people expected. So that's not really visually getting a whole bunch of people around him. So the movie, good movie, and John Nash himself likes the movie. Random fact. Yeah. Like who's Nash? He always claimed that he's a mathematician. He said he like when he got the like Nobel Prize, he didn't even go and pick it up like himself. Because he insists that he is not an economist. He is a mathematician. And also, like later on, he also won the it's like the Apple Prize, yeah, Apple Prize, which is for the mathematician one. That's when he really went there himself, because he considered himself a mathematician always. And if you see like what I got here, this is one of the like most famous recommendation letter from any given person, which talks about like, hey, like Mr. Nash is 19 years old and is graduating from Carnegie Tech in June. He is a mathematical genius. And this letter got him accepted. So, well, that's something which kept as like a legacy after all. But in between, like Nash's career kind of got disrupted since he can't really teach like normally. So after a few years of like getting like trained and with therapy, he kind of returned to school after about like 20 or 30 years ish, which is like a really long gap. And since then, he's still working on like solving a whole bunch of different things, including like Nash equilibrium. It's not called Nash equilibrium in his own thesis. It's just called equilibrium. And his idea is it's a competing equilibrium which people will not deviate from. So this is one of what he did. The other thing is called a bargaining power, which is Nash bargaining. What is Nash bargaining? It is about, remember we have the producer surplus and the consumer surplus, right? But normally in different cases, we just simply talk about this is total surplus. We can't really find out where the demand, where the supply looks like. So we know how generally, what is the full profit above. So remember P minus MC, that's the idea of markups, right? So how do you split the markup between different people, different parties? That could be a math problem, and that's also solved by Nash. It's called Nash bargaining. You will learn this if you're doing more of the like industrial organization, IO related features. Okay, so that's things about Nash. And of course, like since Nash, in between, he thought he's hearing different voices, and he's just like wandering around Princeton, writing things on blackboards, writing different questions all around the place. So he's also called the Phantom of Flying Hole at the time. I had a professor who was John Nash's student. His name is Reza, back at Johns Hopkins, professor in the School of Engineering. He did tell a fun story I'll share with the class. Which is students always start writing John Nash's like handwritten stuff on the board. But when everyone else like in Princeton figure out like, I think something's missing in between, they ask Nash and Nash kind of yell them out. Like, don't ask me, I'm not going to answer this. One day, when someone's like in the washroom, they found Nash standing next to them, and Nash is just like talking when he's like using washroom all time long. Then someone secretly took a notebook, and since like John Nash said something, he didn't even say break time. He just walked out of the classroom. The students followed him with a notebook, writing everything he said. Coming back, they figure out that's where the missing piece looks like. So yeah, that's just like random fun story to be told about. He is actually lecturing every single minute, every single second, but people didn't know that. They thought like the time he walked in and out was the time of the cutoff, but it's not. Yeah, that's some fun things happened which in Princeton about like more than 20 years ago, I'll say. Yeah. And yeah, he passed away like 2015, right after getting an Apple Prize, coming back to US and caught in a car accident. That's when my classmates said things about, oh, I read the textbook. I never knew he was alive, and I felt sorry that the first time I knew he was alive, he's dead. Yeah, that happened to Nash. But well, a legendary. So that's why now talking about everything game theory, there's always Nash. Okay, yeah, that's a fun story about Nash. Yeah, 5 minutes, great. So I will go through a little bit more of simultaneous games. the stack hunt part and the decision rule parts about if you have multiple Nash equilibria, what will happen. And after those parts, we'll take another 5-minute break that you can walk around, stretch, and everything. Okay, good. Okay, so stack hunt. So there will be the stack and the hare, right? Stack stands for you're hunting down a deer, you've got tons of meat, it's like 5 and 5. If you're hunting hare, it's just like one unit of meat for your family, nothing else. And if someone go for the stack and the other one go for the hare, the stack will not be caught and it will run away. So in this case, stack versus hare. Think about it. Okay, so first of all, always ask yourself, is there a dominant strategy? Let's take a look. If someone else pick S, they're like, yeah, of course you're picking S, like 5 is larger than 1. But if they pick H, you are picking 1 since 1 is larger than 0. Same thing, if you are picking S, they will pick S as well. If you pick H, they will pick H as well. So in that case, we got 2 Nash equilibria, okay? So 2 Nash equilibria, which is stack or hare, okay? So that's what happens here. Okay, so generally, this is a 2 times 2 game. It's called a normal form, or reduced form, or a simultaneous form. It has so many different names. Just remember, the number on the left always belongs to someone as player 1. The number to the right belongs to player 2. That's when you got a 2 times 2 game, or n times n games for like limited number of decisions and limited number of players. Okay, so well, now we have 2 Nash equilibria. How do we choose? If you took my class before, you're like, yeah, we can just do a mixed strategy. Leave it to the computer and give it like a probability distribution. But of course, sometimes it's not that simple. Sometimes it's about human beings. How do you think? So there are different ways of doing it, which goes to decision rules. So in our class, we are only covering max and min. Hands up, we are only covering max and min in this class. What does it mean for max min? Max and min stands for think about what is the safest option ever, okay? Now let's think about if you're going on stack, but the other one's not picking that, you drop from 5 to 0, right? So that's horrible. But in other words, if you're picking hare and they pick stack instead, it's okay. It's not even that bad. So that's generally the idea of max and min stands for what is the worst scenario if you pick S? Let's use a different color. I'll use yellow. If you pick S, the worst scenario is 0. But if you pick H, the worst scenario is always 1. 0 versus 1. 1 is larger, right? So the minimum things from S is 0, and the minimum for H is 1. So 1 larger than 0, so the max min solution will be H. In this case, they are actually symmetric. So we know HH is not only the max min equilibrium, it's also max min Nash equilibrium. So there are 2 things. Sometimes you got something else, which is, for example, if you play, what are they? If you play things as, let me think. If you play chicken game, for example, if you play chicken game, the max min could look a little bit different. The game of chicken or chicken game. So which is, okay, I'll get like move forward or turn, F or T, forward or turn. And we all know that the game, if you move forward together, you bump into each other. Let's don't make it something like that. Let's make it nothing good. If both of you turn away, both got 5. And if one turns away and the other one moves forward, the one moves forward got, let me think, got 10. The one turn away got 1. Let's do this. Okay, so in this case, if we're talking about moving forward, if you know someone else is moving forward, you better turn. But if the other one is turning, you better move forward. The same for the other ones. This also belongs to 2 different Nash equilibrium, right? Okay, but in this case, let's look at the maximum rule again. So if you're picking F, you're comparing 0 and 10, and 0 is like the better option, right? And if you're thinking of t, it's 1 versus 5, right? So in this case, you'll pick t, right? Also, for the same rule, if you know the other players also, like if you don't know, the other players also playing max and min, they are thinking like, okay, 0 compared to 1. Sorry, let me think. Sorry. Am I going a little bit, wait, 0, 10. Oh, sorry, this one's like 0, if I pick F, 0 smaller, if I pick Z, okay, yeah, right. If I pick F, the smallest value I get is 0. If I pick T, the smallest I get is 1. So because of that, I'm picking T, okay? So in that case, both of you are picking T's. So you are getting the turn solution, which is not a Nash equilibrium, okay? Anyone who doesn't know why this is not a Nash equilibrium, please let me know. Anyone? Everyone know why, right? Because this one doesn't belong to the best response of anyone else. It's just simply because I'm afraid of getting hurt too much that I go with the pessimistic way. So that's how both pick to turn, and you got the 5-5 equilibrium. But is it real equilibrium? We don't really know. It depends on how the content looks like. Okay? So we just need to know there's a maximum equilibrium, and sometimes maximum is also a Nash equilibrium called maximum Nash equilibrium. This is covered by the class. Okay, got it? Any questions about this? Yeah, if not, I'll just simply go through different things. This is maximum. You're like, hey, they're just afraid of making a decision, right? There is also maxi-max. What does it mean? I always take the largest possible error thing on this board. So 5, poof. Then 5-5, this will be the maximum Nash equilibrium. Not in their exam, but get to know this happens. Same thing. If they think of maxi-max in this case, they're like, I have a chance to win 10. Why not playing forward? And boom, they got 0-0, which is also not Nash equilibrium, but also something under a decision rule, maxi-max. There's also a third thing which I just listed out as a reference, which is called minimax regret. So what does that mean? Which means that when you pick something, you look around and like, too bad. If someone else is going to change their decision, actually I'm going to win a lot. What happens is like this one. If you pick H and you got 1-0, you got that 1, you're happy. But the thing is, you're regretting that someone else is picking S, right? So like, hey, if I pick S, then I'll get 4 more units. So your regret is 4. That's a huge regret. And if you're playing a 0 and 1 and you're playing the 0, you're like, oh, if I move there, I got 1. Your regret is 1. So compare the max regret of S is 1 and max regret of H is 4. So the minimum of the two, you will pick S. So this is just some other decision rules. If you take more like business-related classes, you might face them. But you just get to know, generally there are more than 3, but the 3 most famous ones, maxi-min, which is be super extra careful and pick the one you'll lose the less, like the least. That's what we learn in class. But there's also maxi-max, which is the optimistic version, and the minimax regret, which is you're thinking of which of these ways you're not regretting the most. If someone even someone's not changing their mind. Okay? So exam, maxi-min. Get to know that. Okay, so I'll keep the stack hunt thing on the blackboard for a bit, this one. And let's take a 7-minute break instead of 5. So we'll go through the mixed strategy Nash equilibrium once again. And we'll come back by 6:05. And we'll move forward to something which are not taught yet, but good to know, and maybe even in exams or something. Okay? Be back 6:05. Okay, it's time. Okay, let's continue. So right now, I'm going to talk about the same game, stack hunt. But instead, let's take a look at the mixed strategy. So last class, I kind of walked through this. So today, I'm not going to use too much time on it. Mixed strategy is the point you want to figure out when you leave your decision to the computer or someone else or anything else for a randomization. For example, I give 50% stack, 50% hair. Leave it to the computer and you're like, let me come back later and figure out what the computer chooses as my decision. Yeah, that could happen. For example, if you're playing like rock, paper, scissors, shoot, you're like, let's do 40%, 20%, 40%, things like that. You can actually program it into a laptop and it kind of like repeats something as what you will play. Now we're just going to find what specific percentage will it look like for the other player to feel indifferent. Okay, that's what I kind of mentioned last week. So let's take a look. So now, given that player 1 is playing A and 1 minus A, so A for hunting stack and 1 minus A for hunting hair. So how do player 2 feels like? So if player 2 now picks S, player 2 will get 5. What? The 5 belongs here. 5 multiplied by A, right? 5A. This stands for the probability that the other player will place like hunt stack as well, plus 0 times 1 minus A, which stands for the probability that the other one will hunt hair. So this will be player 2's S, okay? Same logic. You'll get 1A plus 1 multiplied by 1 minus A. This is player 2's H, okay? The decision rule is you want the rule to get your mixed strategy two to be equal. You want them to be equal. So in that case, the first one is 5A, the second one is 1. Okay? So yeah, 5A plus this is 0. The second one is 1A plus 1 times 1 minus A. So of course this one's 1. This is so in other words, 5A equals to 1. If you get A equals to 0.2, then the other one feels indifferent. Let's check it. If A is 0.2, the second player is like, I'll hunt stack. But I got a 20% chance to get 5. So my expected payoff is 1, right? 5 times 20% is 1. And the other one, I don't care about that number because I get 0 anyway, right? How about if I pick hair? So 1 times 20% plus 1 times 80% is still 1. So left-hand side, I got 1. Right-hand side, I got 1. 1 equals 1. Good. So the same logic applies to the second player. So, but instead, they're doing the 5 on the left-hand side. So there's a 5B plus 0, 1 minus B, which is equal to 1B plus 1 times 1 minus B. Okay? So it's the same logic that 5B also equals to 1. So your B star also is 0.2. So if you're not that sure about it, you can look at my handout. This time, you can simply turn to page 7, and you'll see something with a sigma. That stands for specific probability distribution. Everything about sigma, this one's like normally used in master and PhD level stuff. I'm not going too much into why are we going to write things like this, but when you see that, it stands for, oh, this is a mixed strategy. And a mixed strategy belongs to like a probability distribution, okay? Of course, you see sigma, you remember stats, right? Equal to 20, you just finished that, right? So hopefully, remember that. That's why I kind of like make the sigma note up here, which tells you it's a distribution. Instead of giving you one number, it's some kind of possibly coming, like dropping to this point. That's it. That's mixed strategy and equilibrium, okay? So generally, yeah, you can also work on this thing, which is like, hey, which point will we actually pick? Yeah, if that's the scenario, this one's kind of funny, but yeah, maybe we'll leave this as some kind of practice later on. But never mind. Right here, anyone got questions about mixed strategy and equilibrium? It's also a thing that because if I play this point, if I play with this probability, you feel indifferent. If you play that probability, I feel indifferent. In short, let's just leave these probability to the computer and let the computer play for us. And we'll just leave the laptop there, let it run. Yeah, that could be how it happens, okay? Yeah, so this is mixed strategy Nash equilibrium. And you just get to know, this will be the first thing you'll face Masu when you come back from your reading week. And if you're not getting used to the idea of picking the point which the other one feels indifferent, then this was for quite a while, since he's only using 2 to 3 slides to cover it, okay? So get to know this. This is pretty much testable content. If I'm the one who decides, if like your midterm and final exam, I'll make this into both of them because there's some kind of art from game theory, okay? Something else which is not directly written, but if this is in the test, it's still fair. Let's think about this scenario. Instead of 2 hunters, we have 3. What happens? Now we get a even larger stack, and with 3 hunters, all 3 of us need to collaborate together to hunt it down. If any of us ran away, then the answer is we'll miss it. Okay? So of course, now we have 3 players. If we all get the stack, it's 5, 5, 5. If we all go to grab the hair, it's 1, 1, 1. And in between, we got all other options between these 2 numbers. So let me just write them out. Okay, no, before I write them out, think about that. 2 times 2 is a surface, right? 2 times 2 is a table. How about 2 times 2 times 2? It's a cube, right? It looks like a cube like this. So I will say, hey, how do you flatten the cube onto a table? The answer is, as you can, slice them somewhere in between. So in this case, I slice the 3rd player off. How do I do that? So if the 3rd player chooses S, I write them on the left-hand side of the table. If the 3rd player chooses H, I write it on the right-hand side of the table. Done, right? So you can actually do that. And yeah, I'm not going to finish the entire blank, but it's the idea that you can actually think through, if you have 3 players, you're going to do this. But that's just an easier way to do so. Because if Masu says things like, let's do N players, let's do 100 players, you are not going to draw a gigantic table, even before you finish player 1, I think it's already 2 hours. So we wouldn't really play things like that. Instead, what you should think of, number 1, is there a best response? Or is there a dominant strategy? Or if there's a dominated strategy that you know one player will never play? Sometimes it happens. Number 2, if none of these are true, you know that if they're symmetric, sometimes you can find the Nash equilibrium easily. Simply find some numbers which are big enough and ask yourself, if I am player 3, when it says 5, 5, 5, will I move out of this spot? If yes, then it's not a Nash equilibrium. And think about the 2nd player. If they're player 2, are they going to move out of the spot? 5 becomes 1 in that case. So it's also a no. So in other words, if all 3 players are not moving out, this is a Nash equilibrium, okay? So the same logic happens to no matter how many players. It's all about, if we're asking you, if this is this a Nash equilibrium? So you simply switch everyone out to any possible combination. Just switch one at a time. If you can't find them, it is, okay? So figure out if something is a Nash equilibrium or not. And of course, in the exam, you only got 100 minutes. We're not going to do something extraordinarily crazy. But if we're playing around with drawing a to get the solution for that, and this one's symmetric, so it's easier. It's kind of easier. If I make things if the numbers are really different, you get to know that so I'll just simply write out everything related to the SSS. So this is 0, 0, 0, 1, 0, 0, 1. This is 1, 0, 0. This is here. This is here. And anyone? Oh, here. This one. Right. 0, 1, 0. So let's check who are we comparing. So I'll use different colors here. So if all 3 of us are playing S's, if I'm player 1, I got this 5. If I move out of that spot, I'm just simply switching down. So the 5 compares to the 1 here, okay? If I'm player 2, the 5 compared to this 1 on the right. And if I'm player 3, the third 5 compared to, remember, this is everything you choose S, this is everything you choose H. Since these two are different layers, so this is up, this is down, so you're comparing with this one. Okay? So in other words, 5 to 1, 5 to 1, 5 to 1, none of them is profitable, so that's not a Nash equilibrium. Oh, sorry, so this is a Nash equilibrium, okay? Yeah, that's the logic of, if you're drawing them like side by side, this is how you get it. Maybe I'll get some kind of question like that, but we wouldn't know. Yeah, okay. And the elements, and the equilibrium, and the table. Yeah, so hopefully this is all about simultaneous games, which means we play at the same time. By now, we'll come back with something called repeated games very soon. But in between, let's play something else a little bit different. So I'll first tell the story, which is kind of something I saw during my senior high school years. In other words, it's like more than 50 years ago, which is a group of pirates. They got 100 coins. Each coin is like worth like thousands of dollars right out there. And the coins are not separable, so you need the coins to be in full shape. Each coin looks identical. So they came up with the idea that, hey, starting from the captain, each of us propose a method to distribute the coins, like from the captain, the vice captain, like the crew member 1, 2, 3. That's the order. So please decide, how are we going to distribute the coins? The thing is, each of us propose a distribution starting from the captain. If you fail that proposal, then you'll be tossed into the ocean and be fed you'll be fed to the sharks, things like that. So make it for the distribution thing. How do the first player, which is the captain, survive with this entire idea? Let me come with the answer first. The answer is we need to work on backward induction. And the first player can actually find a way to figure out what is the best scenario that for the other four members, at least 2 of them are happy about it. Okay? So we'll talk about this slightly later. And also there's a different story talks about, okay, yeah, there's a group of wolves and there's one sheep. If a wolf eats a sheep, the wolf becomes a sheep. Will you eat it or not? Things like that. And if it's like 2 wolves and a sheep, the answer is of course not. Because if you eat that sheep, you become a sheep, you'll be eaten, and that's the end of the game. So think from the very end. If there's only 1 sheep on the grass, 2 wolves, no one wants to be the last wolf left with so everyone wants to be the last wolf left with a sheep. But if you got 1 more of them, it is definitely possible that you'll be eaten for the very last round. So everything else will be gone and only 1 sheep left on the grass. So if you got 3 wolves and 1 sheep, the answer is you'll eat it anyway, because you'll fall to that scenario of 2 wolves, 1 sheep, and you're safe again. So that's a fun story again, which is if there are multiple wolves and 1 sheep, who will be the one to eat it? Yeah. So that story kind of links to how the huge stations don't really simply start wars. We all know what happens. So yeah, that's how the entire story looks like. And that's called backward induction. We think from the end to the beginning. But before we start with game theory and how different people decide that, first we start with something which is called decision theory. So look at the graph I drew here. I'm not going to draw that on the blackboard again. It takes me 5 minutes or more. The logic is, every single square stands for you can make a decision, yes, no, do not do, forecast, no forecast, right? Yeah, that's squares. Every single circle stands for, it's a probability node. So for those probability features, it is not about you to select. Nature gives you a probability that either goes up or down. So it gives you the probability, like 0.5, 0.5, and you might make your decision the next round. So if you look at this specific graph, then I kind of listed out how you get it. So the story is about a farmer trying to farm, but the problem is they didn't really know if planting will means that they can really harvest. Harvesting means they got $50,000, and not harvesting, if it's a dry season, they kind of lost all the costs and like the labor and everything else. So it will be negative 220,000. So it's horribly like high profitable and high cost. So the thing is, is a farmer worth like paying $5,000 to believe in some kind of forecasting channel? But the forecasting channel is not perfect. So if it rains, the forecasting probability of like if it forecasts rain, that it will have a 90% chance of raining. If it forecasts dry, it's only 80% correct. So in that case, we can actually start. You see, like after paying that $5,000, you still have a chance of getting $45,000 left as your profit, or you lose an extra $5,000 because you forecasted on the very top. And in that case, you can even draw a line like, hey, so in that case, this circle, this dot will give you like a certain number of payout. So the number belongs to page 10. You'll see that, yeah. So page 10, I'll tell you, yeah. So for the very last, like for the node above, it will give you 38,000 expected value. The second node is if you figure out like, hey, it forecasts that it's going to rain. So you rather lose $5,000 and you don't plant. Same thing, if you compare these, like this scenario versus the one below, the one below is like, we just simply decided it's like a 50-50 chance, rain or not rain. Oh, sorry, 55% chance of raining, 45% chance of dry. You don't forecast, like you just simply bet. Yeah, in that case, you get like expected value of something else, which is the first one I wrote as not 4. Like not 4 gives you 18,500. And you take the expected value of the other set that if you pay for the forecasting, you only get $16,500. So in other words, it stands for $5,000 with that accuracy is not even good enough. So you rather not forecast and simply say, just plan it anyway. Make that gamble. Okay? Yeah, so that's generally what this tree is talking about. Why am I talking about all these things? It's decision theory. It's not even in our class. Because if we're talking about game trees, it's sometimes the same logic. So first, you kind of start with making decisions. Like I'm just going to draw the tree slightly later here. Okay, 2 seconds. Dun, 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 dun. Okay, so first, there will be a specific firm talking about, do I want to enter? Or I don't enter, or I just say exit. That's easy, right? So for each of these points, the second player who's an incumbent in the market goes furious, which is like, I am the monopoly power of this market. How dare you enter? So they're like, do I want to start a price war? So hopefully price war, if you remember from the last week's session, if you have different marginal costs, a price war will cost you something different. But the goal is to kill your enemy instead of really earning money, if it's a per trend competition in this case. So we can go as high price, which is like I don't care, or I do low price, which stands for I start a price war. So the first case is take it in millions. So if you enter and I just do nothing but just take the high price, I will keep $10 million and you get $8 million. The market's lost. But if not, I do low prices because of the per trend competition. Now I'm zero. I lost all my profit. But instead, because you might have some entry costs and fixed costs you can't really pay out, so you got a -2. The other case is if you're not entering in any case, you got 0, but I got either 20 or 0. So this is how you tell a story from left to right. And of course here, you can actually draw like tiny, this is not necessary, but the triangles, like tiny triangles on this end, is just like a best practice for business. Not for school, but for business. Yeah, just a heads up. No circles, because everything's given, right? And this is exit, this is enter. Let's solve this game tree, that's easy, right? So, if you're player 2, 10 versus 0, 10 larger, right? You draw that line, and you trace this back. Okay? The second one, 20 versus 0, I pick 20, right? So, you trace back. Now it's the turn for player 1. So given that the first player knows that, the second player will always play high. So you compare. If you enter, you got that 8. If you don't enter, you got that 0. So 8 is larger than 0, you enter. Okay, good? Oh, good? So this should be something easier. But why are we talking about this? Because sometimes when someone else tries to enter a market, the other ones start yelling, if you enter this market, I go on price war with you. So it sounds like horrible, but do they really want it? The answer is, compared to 0 profit, they rather still earn something, right? So you know that even though that sounds harmful if you got a -2, if it's a million, -2 million for a firm. Yeah, it might look bad, but if they are smart enough, they don't really kill themselves by taking that 10 million off their market, right? So because of that, you know that, yeah, they might threat you with that 8, with that price war, but we don't care because 10 is always larger than 0. So even though they claim that they want to do it, they wouldn't. That's called an empty threat, okay? Which is something which sounds like it will block you from entering because -2 seems to be larger than 0, smaller than 0. But the thing is, you know they wouldn't play that. So it's an empty threat, okay? Now that's generally about the part of when decision theory comes with not only 1 player but 2 players, you need to label them like clearly on where they are playing. Who's number 1, who's number 2, okay? Yeah, this is like a better example anyway. But of course, I can show everyone something else. So here are 2 things which are not really covered in class, but good to know because you'll face them anyway, and hopefully next year or so. Which is, if you got 2 players, like a prisoner's dilemma, the thing is you play simultaneously in some ways, or it's nearly simultaneous, but there's still someone before, someone's after, right? Because, for example, there's only 1 police like really in that room, like asking questions. How does that matter? The thing is, the second player is not observing what the first player is doing. If that's the case, you can draw a dotted line between, stands for I don't know anything before me, okay? Or you can draw a huge dotted circle to circle everything else like that. It depends on whose class you're taking. Like Anchor-Tree loves like this thing. I think Colin loves the dotted line itself. Oh no, Colin loves the dotted line. So different professor got different preferences. Just get to know anything with dotted lines around that place stands for I don't know anything beforehand. Because of that, you cannot decide different strategies. Okay? So this one is like silent testify. If this is dotted, you can also only do S and T. Because you don't know what happens until this day. So your decision after that point shall be exactly the same no matter what happened before you. Okay? And since these 2 happen nearly the same time, you can consider, since you have no information, in the long run, they are just like they're having the same time, right? Because if you're playing simultaneously, you also have no information about someone else. So in that case, you can draw this game tree into this table. Okay? Yeah. So that's the general rule of game tree versus tables. Now, let me go. Okay, still got time. So let me talk about one thing which goes a little bit deeper into this. This is covered in the other ECO200 class, like AJ's class, but not our class. So it's okay. In ECO204, 2 out of 3 classes shouldn't cover this, which is subgame perfect Nash equilibrium. So this one, just listen. You don't really need to take tons of notes. But the thing is, let's talk about what this 8 and what this 10 means in the game tree, right? So yeah, people may think this is how originally people might think. You might think that it is like enter, exit, and you might think it's high, low, right? Yeah, generally that's how people think in the beginning because it looks kind of direct, right? Like, yeah, 4 numbers, I just put them into these 4 blocks. But the problem is, how do you show that you have the information? So if I write it like this, which stands for I have no information in between, right? But the thing is, if I have information in between, how do I show that information? The answer is, now you need to split your personality into two. So this is like 2 enter, like 2n, and 2x and 2x. So instead of high and low, we need to think it a little bit more complicated, which is, you need to think both. If I see you entering, what I will do. If I see you exiting, what I will do. So this is like two different things. Yeah, okay? So this is n, like I do high when you're exiting. So high, low, low, high, low, low. So instead of 2, I need to write 4 different things out here. So this is how you draw this kind of extensive form into like a flat table. In this case, it's kind of easy to talk about like entire things. So I think I kind of drew it on. I wish I drew it. If not, I'm going to write it. Yeah, perfect. It's page 14. Page 14. So of course we know like if the first person exiting, they always start with a 0. 0, 0, 0, 0. And if they do low prices, they also end with a 0. And high prices, they got 20, 20. Like 8, 10. 8, 10. This one's like minus 2, 0, minus 2, 0. Okay? Of course, in this case, you're like, yeah, that's still Nash equilibrium. Da, da, da. Dum, dum. I remember I got that. Oh, never mind. I'll just do it myself again. Taking this, 8, 0, 8, 8, 0, 8, 0, 0. So no dominant strategy, I go like this. The other way, like, okay, so if playing EN, like HH and HR are both good. If playing EX, these two are both good. So we have 3 Nash equilibria. Okay? So the Nash equilibria stands for enter, high, high, which exactly is what we're playing right now. This one will also, since we can draw this out exactly, this one is also SPNE, subgame perfect Nash equilibrium. Okay? Why? Because each of the nodes which you have perfect information, I consider is some kind of subgame. This is player 2 playing a tiny game of picking high or low. I like high. That's it. That's a game player 2 playing because it's a subgame. Same thing for the player 2 when the first player exit. I'm playing high or low. It's a subgame which they also play. Okay? So it's a subgame and it's perfect because you get all the scenarios and you got the perfect information. And it's a Nash equilibrium since it's a Nash equilibrium here. Okay? But of course, there are scenarios which is also called Nash equilibrium, but it's not subgame perfect. For example, high-low enter. Like I play high here, I play low here, and you enter. Yes, we don't really go this way, but 20 is still larger than 0. This is just a scenario which shows that compared to the other scenario that like, oh, okay, so this is entering, but if you exit, I got like a 0, and I prefer that you'll enter. So this is kind of an empty thread. So is the other one. Okay? So if anyone asks you, how do you mathematically show the empty threads, which is write the entire strategy set out and pick the one who are not subgame perfect Nash equilibrium and say they are empty threads, which is like, hey, I play low, high, and you will exit. I play low, high, and you will exit. This seemingly is good because, like, of course, if you switch from exit to enter, you'll actually lose more, right? Because it's from 0 to -2. But it kind of ignores the fact that this low, high, all belongs to the same person. So you can, without switching different, like, without switching further, yourself could actually figure out what happens beforehand. So claiming this is an empty thread. So which is, if you draw this table out and you circle Nash equilibrium, but it's not a subgame perfect Nash equilibrium, it could be an empty thread, okay? So not that important, but it's just good to know that how do people show strategy versus actions? And here is why I tell you, I'm going to talk about action and strategy as different things. L is an action. This L is also an action. This H is an action. This enter is an action. HH is a strategy, LL, LH, HL are strategies, okay? So that's how you separate what we call strategy versus actions, okay? Not in the test, optional, but good to know. And if you're like, Lawrence, I missed your last 10 minutes, like, never mind. It's just good to know. It's not about you need to remember this. But if the other ECO200 students tell you that they know what subgame perfect Nash equilibrium is, this is what they learn. Yeah, that's it. But right now, everything you need to do is right here. And also, the other thing is, if I'm talking about, like, for example, Stackelberg model, I'm picking a P. So P can be, a Q. Q can be 100. Q can be 99. Q can be 98, all the way down, right? So imagine that you got infinite options. It looks like this, right? So the right way to draw out continuous options is like a shape of a fan with a radius, okay? Yeah, this means continuous. Options as action. Not sure if Masu is going to teach this, but just get to know. Like for Stackelberg, like this is like this happen like this, and for this point, you got player 2 also giving you another fan. So this is like Q1, this is Q2, and this is the point that you come up with a solution. Okay, and you got some kind of profit 1, profit 2. Okay. Yeah, I'm just writing it like super ugly, but just get to know if everything you know which are not really from the class are, say these three. Like one thing, dotted line for no info. Number 2, the fan for continuous options. Number 3, subgame perfect Nash equilibrium matches the graphs. This one. Okay, those are the 3 things which are not really in your test, but good to know. And also, the way we solve subgame perfect Nash equilibrium from back to the beginning is called backward induction. So let's come back to the pirate question. Now, okay, this is the fun part. Once again, so now we know if today there's only 1 pirate left, what will happen? You will give all the money to yourself, right? So no one else is there. They're all fed to the sharks. But if there are 2 players, what will happen? As long as you have half of them agree, which stands for if there are only 2 players, you rather get all the coins because there's only 1 other left. Like, you're not strong enough to push me down for the sharks. So I will take all the coins. Think about that. So I'll erase this word. Let's just look at it from the back to the beginning. So 0, 0, 0, 0, 50, 100. So this is the perfect scenario for player 5. And to show that who's already killed, I'll draw this. Okay, so in this case, you understand that if the first 4 are all killed, this will happen. But on the other hand, the number 4 player will not be killed actually. And instead, the number 4 player will say, I want 100 coins. This happens if the first 3 players are all killed. So now, player 5 is thinking, if I actually had any strategy which accidentally killed player 3, I would have nothing, right? So let's think of the scenario of if only 3 players are left. So player 3 is like, I want to survive, so I need to give player 5 something. So instead of giving 100, they're thinking about the 0. So if player 3 is killed, player 5 got 0. But if player 3 is not killed, let's just give anything larger than 0. Let's give you 1. 1. And player 3 got 99. And player 4 got nothing. So, of course, player 4 is not happy. So player 4 will vote that player 3 need to be tossed into the water. But actually, nothing happened because player 5 is thinking, if I do this, it will be only me and you, and I got nothing. So 1 is better than 0, so it's okay. Yeah, so this is accepted by player 5, right? Okay, let's think the next stage. If only the captain is tossed into war. So it happens this way. So then 99, 0, and 1 belongs to the other player again. What happens here? Think it this way, which is, now player 2 is thinking, if I give player 4 anything larger than 0, player 4 will vote that I shall stay on the ship, right? The other players might go against me, but it's 2-2, I will still survive. So 99, 0, 1, 0, it's okay. Yeah, perfect. So now back to the captain. The captain is now thinking, let's just give these 2 guys 1, and the other 2, let's give them 0. Why? Because let's just compare. 1 is better than 0, so I get the vote from player 5. 1 is also better than 0, so I got the vote from player 3. And I got the rest for myself, so I'm alive now. Because if I got tossed into water, these 2 got nothing. And the second player is thinking if I got tossed into water, this guy got nothing. And the same logic, if player 3 is if I got tossed into water, player 5 got nothing. The first player is I want to get tossed in water. This never exists. So I'll take all the coins. So in the end, the answer is, how do you make a distribution? The proposal is 98, 0, 1, 0, 1. Poof. Solve it, okay? So this is just a fun little story about how do you distribute coins. So you think from the very end of, if everyone else just got tossed into water, what would happen? That's the end, right? Think step by step back as, what will be good enough that someone else will at least they'll vote for me, otherwise they will lose even more. So that's compare 1 to 0. So in that case, they survive, okay? And backward induction, normally there's a word called first mover advantage, because look at this. You're player 1, you can decide what you want to do, and you got 98 instead of everyone else getting 0s and 1s. You have the advantage. Yeah, that's how we normally say things. Of course, there are some things which, if we play continuously, you have no advantage. For a really good example, whoever wants to play first, if we're playing rock, paper, scissors, shoot. No one, right? Because I see you playing, I can't do anything else to conquer the game. I know what you're playing already. In that case, first mover got disadvantage. So not all first movers win the game. It's not like matching penalties or penalty shoot. If it's first I decide to shoot the left and I'm running toward it, I'm kicking this way. And I'm having my leg up here, and now it's your turn. You can have 5 seconds to run. Of course I'm shooting there, and I can't because of the gravity and everything else, I can't move to the other side. You can block me out right there. So in that case, matching pennies is also a game that you wouldn't want to be the first mover. Instead, you want to play it either simultaneously or be the last mover. Yeah, that could happen in some cases. Okay, so that's it. That's the entire thing about how do you get trees like this. And of course, when we're talking about these things, remember, I kind of solve it from the back to the beginning. But when we're talking about a story, talk from the beginning to the end. That's how we kind of explain things. Same thing. If you want to understand something called a tree regression in the future, you solve things from the end to the beginning, but when you're talking to a CEO, tell them, what is your first move? If not doing this, something else horrible will happen in the end, right? So when you're talking about a story, start from the beginning to the end, solving them back to the beginning, okay? Yeah, that's everything about subgame perfect, Nash equilibrium, decision theory, dynamic game, and on. So we got one thing left, which is called repeated games. Any questions so far? If not, I'll also talk another one funny thing, which is called the backward induction paradox, which is a professor tells the students, Monday, Tuesday, Wednesday, Friday, Thursday, Friday. I will pick a day that you'll never imagine, and I'll give a random exam to all of you, if I can, or maybe no exams at all. But you will never guess it. Okay, so by backward induction, if I guess Friday, that I guessed it, so no, it wouldn't be Friday. Because if it's Thursday, and I can guess Friday easily, so it will be Friday. But then I guessed it, so the professor said no one will guess it. Let's cross out Friday. It's Thursday left. And by Wednesday, we know that if there's not on Wednesday, we got Thursday left because Friday wouldn't happen because we deleted it. But then it wouldn't be Thursday, right? And it wouldn't be Wednesday. It wouldn't be Tuesday. And it wouldn't be Monday. So no way. The professor will not give us an exam. So instead, he'll give you an exam any day and you're like, I got cheated. So that's a backward induction paradox, which means that if you feel like you can delete things iteratively, then it's just as bad as you didn't delete anything. Yeah. So that's a paradox, and it's something just good to know as well. And it's just a fun little story to get everyone still awake. Okay. So the last thing, which will be in your exam and highly likely will make some questions out of it, because this is something that at least we can try, which is called repeated games. Why am I still keeping this? Why am I keeping the nuke here? Because if you remember, Nash equilibrium stands for is at least playable because no one wants to deviate from it, right? So this is something playable. But in other words, if you're talking about, I thought that minus 5 minus 5 is better than minus 10 minus 10. You can actually propose an idea, which is, let's play a game. Both of us pick silent. If we play infinite times, if we play many, many times in the future, let's try to play something who's not a Nash equilibrium, which gives us somehow a better payoff. But if you dare to give me something bad, I will play the nuclear option to kind of crash everything. That makes sense, right? Because as I mentioned, nuclear option is also Nash equilibrium. It's playable. You can do that, and the other player have no choice, but they can only follow your option. So they are afraid that you will play the negative 400, negative 100. So they need to make a decision if they really want to collaborate and start the silent version. Okay? So in other words, if it is a finite game, which means that you have limited terms, but you have more than one Nash equilibrium, you have more than one Nash equilibrium, you can actually tell them, we know of the two Nash equilibria, one looks better than the other one. So if you collaborate with me, we'll play something which is not a Nash equilibrium, but which is better for all of us. And if you dare to cheat on me, we will play the worst ever option you can ever think of. That's what we call a punishment strategy. Okay? So first of all, you need something to punish people if you're playing finite period of time. But of course, if you're saying, okay, we're only playing two periods, what will happen? Period 1, if you cheat on me, I will play nuke next time. Okay, that makes sense, right? But for the very last period, if I say the same thing, I play silent. If you cheat on me, I'll play the nuke option. It's worth nothing. Because you don't care. It's the very last period already. It's the end of game, end of world. So I came up with the idea of, if there's a tribe that the voodoo witch doctors tell you the tribe will disappear in 3 days. So now either trade or just move around. You're like, okay, if it's the last day of your life or the last day of this village existing, then, well, you don't need to care about any punishment the day afterwards. So in that case, they might still kind of deflect to something like testify in this case, right? So you thought they will still play silent because the nuclear option looks bad, but actually testifying for the very last period is okay. But if you still got 1 period left, they are still afraid that you will nuke them in the very end, so they might collaborate with you. So the idea is, if it's a finite repeated games, it will always end up with some kind of Nash equilibrium. Okay? If it's a finite game, and we're not talking about we're not talking about anything else. It's just any finite game, and we will always end up with some Nash equilibrium. Of course, if there are no nuclear options, no matter how you persuade others, they might not collaborate with you because a way or another, if they cheat you for once, they win 5 units of everything. Then in the future, by backward induction, the logic, in the very end, they will still play testify. And why not doing this for the -2 period, -3 period, and on? So normally, finite games, for most of the time, 2 or more Nash equilibrium. Okay? That's the idea. If it's a finite game, normally it will end with a Nash equilibrium. And if you can collaborate, you need at least 2 Nash equilibrium. Otherwise, if there's only 1 Nash equilibrium, in the very end, you will always play that anyway. And because you'll play that in the last period, when the second to last period, you will also play that. The third to last period, you'll always also play that. But by backward induction, you will not collaborate. So normally you need 2 or more Nash equilibrium. Okay? So that's for finite repeated games. Also, there's the infinite version of it. Infinite. Same thing. If you have more than 1 Nash equilibrium, you can form the punishment strategy easily. But also, you may think about the other scenario, which is with is cavity. We call it delta normally. Might collaborate. And this one happens like even with 1 Nash equilibrium. Okay, so what is the logic? Just think about this. For example, if today you're talking about something in the future, every single day, like in the future, gives you a discount of delta. It's just the idea of like, okay, I got an ice cream. It melts like 20% every single minute. Yeah, I know, it's not melting today, but never mind. So your ice cream is melting like 20% every single minute. So you can actually find that discount over time, right? So same for this game. Think about this. So today, if we don't really have nuclear option, let's just remove the nuclear option. Yeah. Let's just expect this to never happen. We just have 4 things, which is, okay, so this is ST, ST, okay? ST, ST. And both silent is like -5s. Both T is like -10s. And if it's like 1 each one, the silent one got punished even more, and 0 -20. How do you do things? If it's infinitely going, there are multiple different ways, and I kind of wrote them all out. Like tit for tat, like tit for 1, 2 tats, and there's like the pull off or something. Never mind. So there are different ways of talking about, hey, if you are not collaborating with me, you will get punished by this way. Yeah. And the so-called this way is like multiple different possible scenarios. But today, let's talk about the major game we always play, and because why are we playing it? Because it's easier to make it into exams, right? Which is called grim trigger, which means that you like grim trigger, you shoot, right? You grim the trigger, you shoot. So that's about like shooting, like a shooting phrase. So, okay, of course we know -10, -10, this is the Nash equilibrium. And we know that this is playable, right? We can propose that a grim trigger punishment strategy, which means that let's collaborate. If you dare to cheat on me once, I will forever play Nash equilibrium. Okay? Yeah, it's like no forgiving, merciless. Like I will always play Nash equilibrium afterwards. But if we move on like in a soft way, actually silent might be a possible scenario. Okay, so in that case, put yourself into the cheater's shoes. So think about this. Now, you are let's say you're the second player. And they're like, hey, let's do the -5 forever. So you know that so you got -5 for today, -5 delta for tomorrow, -5 delta squared for the day after, So in short, you got -5 divided by 1 minus delta. So this is your total payoff if you... Good? That good. But on the other hand, if you cheat for 1 time, you will get a 0, right? Instead of the -5, you got that 1 0. But 0 just happened 1 time only, which means 0, comma. And starting from the next period, you will always face the Nash equilibrium of -10. -10, -10 delta squared. And in this case, you got a -10 delta over 1 minus delta. Okay? So this is what you get if you cheat. So in other words, if I'm asking, how big is your delta that you will never want to cheat? The answer is you will need minus 5 to be larger, or maybe larger or equal to negative 10 delta. Okay, so which in other words, if the discount factor goes even small, if the discount factor is smaller than 0.5, right? But is it larger or smaller? Larger. Let me check. Larger than that. Yeah, larger. If the discount factor is larger or equal to 0.5, then you will always pick to collaborate, right? Yeah, so now you compare with, I'll color code it. Everything in blue stands for collaborating, okay? The one in yellow is the Nash equilibrium, which is like the one got penalized. And the one in red is a 0, which is cheating. So the logic is, okay, so I'll verbally talk about it. It's like collaborating forever get a payoff at least as good as cheating for one day and starting from tomorrow get punished forever. Okay, so if this happens, then you will collaborate. If you find out that, hey, actually the punishment is not that harsh because my discount factor is super small, I don't care about the future, I just care about today. If that happens, then why not cheating today, right? Yeah, so that's the overall idea of when do you plan to collaborate, when not. And how to find that delta is a common question we can ask you in exams. Why? Because it's always like number divided by 1 minus delta. It's easy to calculate and it's easy to grade. So get to know this, okay? This is the and okay. And if you kind of missed anything, I wrote this info in my notes, and you can take a look at the. Where is that? Yeah, here. It's page 17 is exactly what I'm doing here. Page 17 is exactly what I'm doing here. So just remember, the idea is like one last time. So okay, so I'll erase the pirates. So the entire story is about find delta. And how? Which is the collaborate divided by 1 minus. This stands for forever. Yeah, I'm just being lazy. Collaborate forever is larger or equal to cheat plus, and here remember that delta, punish. Remember, because cheating on that specific day, that day will be the day that they got the information, but they wouldn't react fast enough. But starting from the next period, which is punished tomorrow. Starting from tomorrow, you'll get punished forever. Yeah, so if that's the case, find delta is larger or equal to something. Yeah, that's a typical question, okay? And of course you can practice with this one. This is not even that difficult, which is, okay. If you dare to, we will stay silent, but if you dare to not stay silent, if you dare to testify any one period, we will play the nuclear option forever. Okay, so that sounds really horrible, but it's really easy to solve. That's a practice question for all of you. Any questions? Okay. Oh, okay. So it's perfectly 7 o'clock. So start wrapping your things up, and I'll use 1 minute to talk a little bit more about the algorithmic game theory thing, which I talked about last time. So if you so we can start packing up. So the overall idea is, when do you plan to collaborate? For algorithmic game theory, it's more about like how the collaborative game could happen. If not, it's about I'll stay myself. So it's called, we all figure out what is the price of anarchy, which stands for that you're doing everything on your own. But then the thing is, algorithms got the chance to tell you we can converge to a spot in time fast enough or not fast enough. So in those cases, we're discussing it's two scenarios. One, can we even find a solution? We're not going to find it, but it's about a decision making of yes or no problem. And the second part is, how soon are you getting it? If you take like advanced econometrics in the future, it's also telling you that you need a whole bunch of data to finally converge to specific spots to get an estimation done. But it's the same thing as it happens to algorithms, because it also tells you that the conversion speed is too low, because like, for example, some specific finding algorithm kind of runs slower than the time from the number of players generating like an additional exponential layer. Exponentially stands for it goes like all the way up, and the speed of algorithm kind of goes like maybe linearly or something like that. So after that point or above stands for you cannot find the equilibrium within your within your computer's power. So those are also scenarios that you might talk about if we're talking about something called algorithmic game theory. Let's continue from everything I mentioned last week. And if you're doing algorithm classes, you're doing some CS stuff, and you're interested in that, yeah, same thing. Feel free to talk to me. I'll give you the notes I had before, and this will be something you can play it like for fun during your summertime. And of course, on my website, I'll start like a tiny career-related page to show like, okay, what specific sources you can play around with. So feel free to visit it if you have time. And if not, this is what you should expect from the game theory part of this class, I expect. If I still miss anything, I'll put them in 2 weeks later. But if not, happy Valentine's Day, happy, what is that? Reading week. And happy Lunar, North Atlantic, or Chinese New Year. Okay, that's it. Thank you. Okay. Good. And no